Right, so we were discussing feedback amplifiers last week. We looked at them and we saw that the general amplifier that you had an open loop or yes, an open loop amplifier, and that we could do something called feedback with the amplifier, and the feedback itself did make improvements for the amplifier depending on how the feedback was done. In the course of doing that, we introduced basically 4 categories of amplifiers. Those that take voltage in and give you voltage out. Those that take current in and give you current out. And then the 2 other combinations, which was voltage in, current out, and current in and voltage out. And we saw that there were some applications of those in industry and in some other situations we spoke about. And then we saw how you applied feedback to those categories of amplifiers. So we weren't specifically talking about the circuits, but we were dealing at a sort of higher level, a sort of block diagram level. And we looked at the equivalent circuits for whatever the amplifier happened to be. And we saw that feedback, that again, the feedback was a combination of what you were sampling, which was the output, and you can either sample voltage or current, and you can also feedback either voltage or current. So the feedback amplifier classification had a 2-name connotation. So we had like voltage series feedback or current shunt feedback. And the first word, the voltage or the current, had to do with what the output sampling, well, what was the output that you were sampling. And the series or the shunt had to do with what you were feeding back, right? Of course, we are all talking about negative feedback here because we have said that positive feedback creates behaviors like oscillations and unstable behavior. In the case of making an oscillator, that was something that we wanted. But of course, in the case of an amplifier, it is an unwanted characteristic. So what we wanted was negative feedback. And we took that approach. And then we saw that among the things that feedback can do for you was that it can depend on the amplifiers that had input voltages, that it increased the input impedance. Because if you increase the input impedance, it means that whatever input voltage you're sensing, more of that is going to go into the amplifier. It would decrease the output impedance. Well, so sorry, if the input is current, then the reverse is true. What you want is to lower the input impedance, so more current will go into the amplifier. The output impedances are the opposite. So when you have an amplifier and you're supplying a load, remember the amplifier has an output impedance and you have a load here. If the output impedance is high and you're supplying plenty current, it means all of the voltage drop is going to be inside of here. So what so what you want to do is that when you're supplying outputs, depending on the gist of the output is just get as much signal across the load as possible. So that in the case of the amplifier, when we're on the output side, for the amplifiers that are supplying output voltage, you want RO as low as possible, so all the voltage is dropping across RL. And in the case of the amplifiers that are supplying the output current, you want the output impedance to be as high as possible, so that you develop as big as possible a voltage on the output going forward. So we looked at that, and then the last 2 things that we have to look at would be the gain, to stabilize the gain and to improve the frequency response of it. And there's a little bit here, and we're going to see that appear when we talk about the impedances here. So where are we? Right. And of course, as I said, and if you check past paper questions, and I'm sort of curating some for you all here as well, they're based on the topics that we have discovered. I don't expect you to, those circuits where we look like these circuits and so on, what I said is that I could give you a circuit like this and ask you to identify the circuit and give me some characteristics, what you would expect based on the circuit, and maybe even derive that. But you should be able to draw the like a transconductance amplifier, the equivalent circuit of a transconductance amplifier. That's voltage in and current out. So therefore the input is a Thevenin equivalent, right, which will be a source and a resistance, and the output will be a Norton, which is a current source and a parallel resistance. And then if you have that, to show me based on that what, for instance, current shunt feedback would look like, for argument's sake there. All right? So that these things you should be able to do, because it's fairly simple to reason out. But this sort of arrangement here, I wouldn't expect you to memorize that. I would give you something like that if I were to give a question of that nature. Right? So we were talking about gain. The other two things that we have to discuss briefly would be that negative feedback. Among the many benefits that it provides is also the ability to stabilize the gain of the network, and specifically to make it independent of the open loop gain. So you remember an amplifier, you have an op-amp, for instance, and the op-amp comes with an open loop gain with it. If that gain now, depending on if the temperature of the op-amp, for instance, changes, or the parameters around the op-amp change, that open loop gain may vary. So what we're doing now, if I supply feedback to the op-amp, so like a normal inverting amplifier, for instance, we saw that sketch before, is a feedback amplifier. And with negative feedback, we derived this little relationship that we did, must be about 6 or 7 times by now. So the open loop gain, which is A, if you put it now into our feedback network, that the overall feedback gain is A over 1 plus A beta. Beta, of course, is the gain of the feedback network. And if it turns out that the loop gain, which we said was this beta by A, or sometimes you see it A by beta, right? If that is considerably greater than 1, then for all intents and purposes, that open loop gain now becomes A over A beta. In other words, it translates into now 1 over beta. All right? So changes at this point in time, notice that the feedback gain does not have any A in it, provided, of course, that A beta is much greater than 1. And when you say much greater than 1, we're probably talking about a factor of 10. Right? So if A beta is maybe 10 and above, then the relationship between the AF and A now basically boils down to just that relationship 1 over beta. So at that point now, you see that the open loop, the closed loop amplifier is immune from changes in the open loop gain. So if you have the amplifier and you find that, let's say, A open loop may be changing 10% because of temperature, right? We have, you go into our labs, and the labs are maybe at about 25 degrees Celsius, and you design a circuit, but the circuit is designed to do something outside, right? So it's really supposed to be controlling, let's say, a pump motor outside in some area, and outside in the shade on sunny days in the current climate that we have may get you up to 34 degrees. So you're suddenly going from 25 to 34 degrees, 34, 35 degrees. So the gain of the amplifier changes by, let's say, 10%. A 10% gain is enough to cause you issues if you're trying to control something precisely. And just think of it, you design and you have all your components chosen fairly carefully, and then all of a sudden a temperature variation is causing something like a 10% gain. So here you have, if you have that particular amplifier in a closed loop, in a feedback and negative feedback loop, that you're going to find that that you can make the closed loop gain of the amplifier independent of that change, that temperature induced change, just for argument's sake. All right, so that's one of the great benefits of negative feedback, that it isolates or immunizes, which is a nice word in our current scenario, that it immunizes us against the sort of component variations for open loop gain. Yeah. And then the other thing that it does now is that it changes the bandwidth of the amplifier. And let's see how. This now will serve almost like a little body plot revision here. So if you have an amplifier where the gain is this, so the amplifier is a simple single pole amplifier. And if you recognize this, right, this is in fact a low pass filter, a first order low pass filter, but we can verify it because if you know AS is K omega over S plus omega naught, then to get the frequency response or to draw the board plot, you make the substitution S equal to J omega. And then, so we get here, and then we put it in the standard form, which is something over 1 plus the J, and in this case, J omega over omega naught. So from this, you can see that the corner frequency is omega naught. So if I were to plot the frequency response, this is log omega, and this is the gain, oops, in decibels, of course, right? If I were to plot that, then once the corner frequency, of course, is omega naught. So this is going to, once omega is much less than omega naught, the gain is 20 log K, whatever that is. Once you meet the omega naught corner frequency, it is going to decrease at what rate? Anybody remember? It's a low pass filter, a first order low pass filter. We have one pole, minus 20 dB per decade. Great. So minus 20 dB per decade here, right? So let's apply feedback to this thing now. If we apply feedback to it, then we have the feedback now is AS over 1 plus beta AS. And of course, AS is this whole thing. So it's 1 plus beta by that. And we can multiply this through. So if I multiply this whole thing through, this is going to be 1 plus J omega over omega naught plus beta K. And on top, we have the K on top here, right? So what I do, if I do that, and then I put it back in the standard form, right? So I have the constants, and then I have the J omega over omega naught. And then I now proceed to divide by 1 plus beta K. So this now becomes K over 1 plus beta K and 1 plus J omega over omega naught into 1 plus beta K. Notice this. Omega naught has now been increased by a factor of 1 plus beta K. All right? K, of course, was the original gain of the amplifier. So if you look, this is supposed to be a beta here. So if you go back to the little, where we were drawing all the response just now. All right, go back a slide or two. Right here. So instead of omega naught now, we have omega naught. We have omega naught into 1 plus beta K. That is where the corner frequency has turned up. So the corner frequency is now here, right? So that's part one. And then look at the top bit here now. Notice at the top here now, if I take this in decibels, this is 20 log of k over 1 plus beta k. Now, originally we had 20 log k, right? So notice two things have happened. One, the corner frequency has gone up by a factor 1 plus beta k, but the gain, this bit on top here, has gone down by the same amount. So 20 log k over that is going to be a little bit less. So the board plot, if you draw the board plot now, this is what's going to happen. The flat part is now 20 log k over 1 plus beta, but omega naught, instead of being here, is now has been amplified or magnified by 1 plus beta k, so it's going to be somewhere here. Right? So the frequency response, the straight line response now is going to look like that. So what we've done, we have in fact increased the bandwidth, but we have done it at the expense of the open loop gain. Right, so the bandwidth of the amplifier is increased by the factor beta k, but the closed loop frequency, sorry, the closed loop gain now has gone down by that factor. So you're getting a trade-off here. You're getting increased bandwidth, but you're at the expense of the gain of the system. And I don't know if you remember coming across or being mentioned to you in level 1, something called the gain bandwidth product, right? That is why the amplifiers and op-amp makers, for instance, give you this thing called a gain bandwidth product, because what happens is that as you tend to increase the gain, the bandwidth drops, or if you increase the bandwidth, the gain drops. So you have to kind of work within those parameters to see exactly what you want. So you can get high gain but very small bandwidth, or you could get very wide bandwidth but at lower gain, right? So it's a trade-off, and this is actually the reason where that gain bandwidth product comes out. The factor is a constant, the 1 plus beta k. So as the bandwidth increases by 1 plus beta k, the gain goes down by the same amount. So in other words, more or less the gain bandwidth product remains the same. So you're trading off gain as against bandwidth all the time. Yeah? Make sense? Right, so those were the last two topics that we needed to finish off. Last week, we had spent some time deriving all the impedances and so on. So to put the discussion of this on top of that would have been a little bit too much, I think. So this is why I deferred it just for today, to close off everything. So that, ladies and gentlemen, concludes our topic menu for ECNG 2012 for this semester. Right, we've done quite a bit. Well, and luckily all of the lectures are recorded and so on. I'm putting together some past paper questions that are of the type that we covered here, so you'll be able to answer those, and the exam will be similar type questions coming. All right, if you look at the past paper questions, you may see some circuit analysis type questions that appeared, especially on the question of feedback amplifiers and so on, that we did not do. It was not part of our course this time. All right, so don't worry about that, because I'm not going to give you a circuit what do you call it, a circuit analysis type problem to do, right? So I'm putting together that. So by tomorrow, maybe later on tonight, if not tonight, by tomorrow, please God, you will get a selection of past paper questions, and by next week, we will make a couple of revision sessions, right? Teaching is supposed to have ended, well, end this week, but the slots are still available. So if you are available to attend those sessions, we will go through the solutions and the concerns that form that I put up and told you not to fill in the wrong form, and then I uploaded the wrong form. But anyway, you could go and check the Google Doc and put in anything that you feel needs some further clarification for you, and we will take it at that point in time. So any questions at this point before we terminate this session and the teaching for this semester? Yeah, we all right? I finished marking the in-course. That is, yes, it was all right. There are more things that I want to do, and the COVID situation, although it was technically possible for me to bring you into the lab, I think what happened is that in order for the lab to be meaningful, we have to be carrying a project through. So I needed for you to start with, like if we were doing a power supply design, to start and we do everything stage by stage so that you actually have something now in place to come in and put it together. I am working on something. I'm trying to figure out maybe early in the semester next time, if we continue along this way where we have where we have a lab day available that people can come in, that I will create a lab of some sort that you can do based on this, where you would actually come in and be able to do the experiments and interact and actually play in the lab environment with it and design or breadboard something that you would have designed before, right? And I'm working on that and working in a way that it may be part of the lab and project design course, so in a way that it doesn't compete with anything else, right? The idea is, of course, for you to build on what you know here without putting extra burden on you for whatever work you're supposed to be doing next semester. And that's a little trick that I have to kind of figure out how to do. Okay, but it's supposed to be. I wanted more practical than this. Maybe the next iteration we could use more multisim and the like in the class, but I had to kind of put this together at fairly short notice, and those kind of things need some assistance that I didn't have at this point in time. Of course, after all of this is done, I would really like you all have access to multisim and so on, and I would really like for you all to, on your own time, before the next semester starts or whenever you get a little break, to actually build some of these circuits in multisim and try it out and see what happens, what works, what doesn't work. Design it on paper, put the thing in multisim, and see if the results match what the theory said they were supposed to be. Okay, and you will learn a lot by that as well. Okay, at least it is one step closer to doing the thing in practice. Of course, if you have access to components wherever you are, it's also great to go and buy some components, get some components, and design a circuit and put it on. Right, little amplifiers are great. You can make those. Power supplies. In fact, the power supply is probably the nicest one to try and do, because it will help you. That is something that you will have to power everything else that you're going to work with. So it might be a bad idea if and when you get some chance to get some components and actually design and make a power supply of your own. All right. Okay, so that's it. Well, we have no class tomorrow, so you can start your revision from now, and I will put up those extra questions. I will also get your results back to you. I'll finish marking in course for this one. So get the results back to you and then figure out how to get your paper back to you, and we will move from there. Interestingly enough, a lot of people seem to have had a little issue with the power supply question. They wanted the fallback protection. I mean, you drew the circuit well because you had the circuit. I guess you could check your notes and kind of copy it across fairly quickly. But then just a quick part after that to specify the components. That it was a very simple step to select a resistor and then just calculate some currents and calculate two other resistors. So it was a little bit disappointing, the effort on that particular question. All right, so if that is an issue that people have something with, I guess that will appear somewhere on our revision list to do. But we will, well, when we meet to do the review sessions and go through some problems and so on, any little issues at that point, well, you could pick up. Yeah. All right. So any last minute concerns, questions, issues? When is the exam, by the way? Yes, we'll go through the common mode rejection ratio. No, the 21st, I think, not the 21st, I think the 20th or the 21st. The one late December is ECNG 2011. ECNG 2012, I believe, in the draft thing I saw is early on, 9th. Right, great. Right, yeah, make sure you study for the correct one on the right there. We'd hate it for you to turn up for the signals and systems exam, or turn up for this one and you really was studying for signals and systems. Okay, so mark it down big on yeah, you see. Right, make sure you study for the correct exam for the right exam on the correct day, or correct exam on the right day, however you want to fill up that. Yes, we'll go over somebody put a question about common mode rejection ratio. Yeah, there was a 5 volt that appeared in everybody's question. I'm kind of curious where that came from. I think you just watched the slide straight off and kind of repeated something that you saw there that wasn't part of the question. All right, but we will get a chance to go over all of those things. We'll have 2 sessions next week to do that. Okay, so let me stop the